Let's start with a single data point, 99.9999991%. That's the percentage of the speed of light that subatomic protons are accelerated to, all inside a 27-kilometer underground ring. And this all happens within a machine of extremes, the Large Hadron Collider. Its entire purpose is to generate 1 billion collisions every single second, trying to recreate the conditions right at the birth of our universe. You know, a purpose like that, it naturally led to a very big question, one that people all over the world started asking. Could these collisions actually create a microscopic black hole, one that could, hypothetically, consume our entire planet? To really wrap our heads around this potential threat, let's use an analogy. Imagine a black hole with the mass of a 3,000-kilogram rhinoceros. That singularity would be no larger than a single proton. So the first reason this fear doesn't really hold up comes down to the physics of gravitational collapse. You see, to create a black hole, you have to crush matter so tightly that its own gravity becomes an inescapable trap for light. And right away, we hit our first major hurdle, a quintillion-fold energy gap. Standard physics tells us that forcing that kind of collapse requires 1 quintillion times more energy than the collider can even produce. The LHC operates at 13.6 Teraelectron volts. Now that's roughly the kinetic energy of a flying mosquito, just concentrated into 2 tiny protons. It's an immense amount of energy for that scale, but it's just fundamentally not enough. Okay, but you might be thinking, what about the what-ifs? We do have to account for a theoretical counter-argument. What if our universe has extra hidden dimensions? If it does, they could, in theory, lower the energy needed to create a black hole, maybe putting it within our reach. And that possibility brings us to the second and honestly more definitive part of this analysis. Let's just assume for a moment that a microscopic black hole could form. Even then, it would be a completely harmless singularity, and the data shows us 4 distinct reasons why it poses absolutely no threat. First off, it would destroy itself almost instantly. A micro-black hole would immediately start losing mass through a process we call Hawking radiation. It would just evaporate in a tiny burst of energy, completely vanishing in less than a trillionth of a second. Second, we have to remember just how incredibly weak gravity is. I mean, on this tiny scale, it's by far the most feeble of the fundamental forces. Think about it. A simple refrigerator magnet can defy the gravitational pull of the entire planet Earth. So the gravitational tug of a black hole the size of a proton, it would be completely imperceptible. Third, there's simple electromagnetic repulsion. Since the black hole would be formed from a proton, it would have that proton's positive charge. As a result, the positively charged nuclei in any surface, say the floor, would just repel it. It couldn't sink. It would just sit there, like any other speck of matter. And the fourth reason? It's just pure and simple odds. An atom is overwhelmingly empty space. A good way to picture it is a single marble sitting in the middle of a huge sports stadium. The chances of a proton-sized black hole ever even colliding with another atomic nucleus are, for all practical purposes, 0. So those are 4 really solid physical principles that make a comprehensive case for safety. But the final piece of evidence, the real kicker, isn't theoretical at all. It's observational. It comes from an experiment that nature has already been running for a very, very long time. You see, for billions of years, high-energy cosmic rays have been slamming into Earth's atmosphere. These natural collisions are happening constantly, and many of them have energies equal to or even far greater than anything produced at the Large Hadron Collider. The key data point from this ongoing natural experiment is simply the continued existence of our planet. The bottom line is, nature ran the experiment first. So because these millions upon millions of natural experiments have never once created a catastrophe, the conclusion here isn't based on theory. It's based on verifiable observational proof. The calculated certainty of the collider's safety is 100%.